In this lesson, we're going to zoom in on the MapReduce paradigm. We're going to talk about what it is and how it works. It's a paradigm that's been used in software for years. It's also in use in NoSQL engines, especially document databases like MongoDB and CouchDB. There's also the possibility to run map-only jobs. We'll look at what those are and how they differ. We're also going to take a look at how to determine the proper number of reducers for an individual job. First of all, let's talk about MapReduce. MapReduce basically allows for parallel processing. If we can fit an entire dataset on one single computer and it works reasonably fast to process that file, then we should never use a distributed system. Distributed systems are going to involve more complexity and are going to shake things up a little bit. The real power of MapReduce is spreading the map tasks, or the logic that we're trying to accomplish, out over many machines so that we spread the load. We may possibly have hundreds, thousands, or maybe even millions of mappers running. Each of these mappers is going to process a small subset of the data. The reduced tasks then join all the mapper outputs. This is an aggregation function, which basically makes it look like our entire processing system possibly only ran on a handful of machines. We use reducers to either achieve a specific number of job outputs, such as temporal, like day of week, month of year, or organizational, such as salesperson, sales region, division, and so on. Or we simply want to spread the loads, because the work can't all be handled by a single reducer. If we have hundreds or thousands or millions of mappers running, all of the output of those mappers oftentimes won't fit into a single reducer, and we'll have to use many. We may also want to use many reducers to simply speed up the reduce function. Even if each of the reducers can handle the data, we may just simply want to add more reducers so that our entire job completes faster. For a MapReduce job, we will absolutely have one or more mappers, and we may have 0 or more reducers. The reduce function, again, is optional, and we'll talk about why. With map-only jobs, we should note in Hadoop that the mapper's output is the job's output. Any output that the mappers write will go back into HDFS. With a full MapReduce job, the reducer's output is what is written back into HDFS, and the mapper's intermediate output is thrown away. As we said before, MapReduce is a paradigm that has existed in software way before Hadoop came around. For example, Python has a built-in map function. PHP has a built-in array map function, which we'll actually take a look at real quick. With PHP, I could, for example, create a function called squareMe that accepts a number as a pass-in, one single number each time we call the function. And then I simply return that number multiplied by itself. I could then set up an array of numbers. In this example, we're using 2, 4, 6, and 8. And then I could use PHP's array map function. With PHP's array map function, we first pass in the name of the function that we're going to call, and then we pass in the array of the data we want to work on. This works the exact same way a map function does. It takes every value in this array and passes them one by one to this function, so that our final output would look something like 4, which is 2 times 2, 16, which is 4 times 4, 36, which is 6 squared, and 64, which is 8 squared. This is simple and easy to understand. Let's look at a more concrete example using a reducer. In this example, let's say that we start out with an empty array called array totals. Then we define a function called add sales, which accepts a region such as APAC, Europe, Africa, and so on, the number of this individual sale, and then a handle to the array totals array. Inside of this function, we're then simply taking that array totals and setting the region to the value of this sale plus what was ever in there before. This function's sort of like a reduce function. Now when we set up our array, in this case we're saying US has one line that's $24, Asia has another line with a $3 sale, the US has another sale with $82, Europe had a $63 sale, and then Asia finally had the last value, a $55 sale. We then run sort of a map function in which we take these key value pairs inside of this array and pass them one by one as the region and a single sale. This map function then simply calls add sales with the region, the single sale, and the array totals. The final array totals would look something like this, where the key value pairs are now the US has a total of $106, Asia with 2 sales had a total of $58, and Europe with a single sale had a total of $63. This sort of functions like a map reduce. The thing is, there's not really much value in doing this in a single system. Sure, that array map function is handy, but wouldn't it be much more powerful if instead we had a set of mappers that we broke out so that we processed 1/10 of all those sales on a one machine each, using a total of 10 machines? Now you can start to see the power of MapReduce. Also, what if we made each of the 3 reduce machines handle the US, Asia, and Europe regions specifically? We would then get one output file for US, one output file for Asia, and one output file for Europe back in our data set. Again, we're not trying to solve a complex problem here. We're just trying to talk about what MapReduce is and introduce it in a way that's easy to understand. This is the true value of MapReduce, taking a single problem, such as summing up the sales in a file, and breaking it up so that we use many machines in parallel to accomplish the mapper phase, in this example, maybe 10 times faster than we could have accomplished on a single machine. And the reduce phase, which now, if there was even distribution among the values, so that US, Asia, and Europe each had a rough number of equivalent sales, we would complete our reduce phase roughly 3 times faster than on a single machine. The other nice benefit of MapReduce in Hadoop is that we end up with one single file for each of our sales regions output. MapReduce, as we said before, is also heavily used in NoSQL. There's a lot of NoSQL engines that use MapReduce to serve up their queries. These engines simply break the query up amongst many query nodes so that the operation completes faster. It's very similar to how database sharding works. You take a problem, break it up amongst many machines, and then aggregate the results set back into one cohesive data set. As we said before, the reduce phase is optional. We can have map-only jobs. Some tasks, for example, require no aggregation or reducing. Some examples of where we might want to use a MapReduce job is when we're simply trying to move data. We may just want to take 4 mappers and make each one responsible for moving 1/4 of the total amount. This is exactly what Scoop does, and in other decks, we talk about how Scoop works. It basically uses a map-only job to go in and query the database and pull out maybe 1/4 each for each of those mappers of our total data set. Another place where map-only jobs is used a lot of times is whenever we're trying to do transformations, and especially image transformations, such as watermarking or thumbnail generation. With image transformations, all we really care about is that each image is transformed as it need be. So in our case, each mapper could simply take the source image, apply a watermark, or shrink the image, and then write the image back out to our local file system, or maybe HDFS or Amazon S3. There's no final aggregation that needs to happen in this phase. Data cleansing is another place that we see map-only jobs working, in which case maybe each mapper simply passes through only the valid records, and we're trying to get rid of missing and malformed data in our input data set. In Hadoop, we generally leave the decision of how many mappers to run up to Hadoop. Hadoop by default uses one single input split, which is usually a single block, as the input to a single mapper. This ensures that local data on that disk where the mapper is running is getting pulled in and then processed by each individual mapper. For example, if we had a file that had 10,000 blocks inside of it, we would end up with 10,000 mappers by default in Hadoop. The user can override this if they choose, but if you do this, you're sort of breaking or misusing Hadoop. By using anything other than a single block as input to a mapper, you're forcing Hadoop to maybe shuffle bits across the network rather than local disk. The number of reducers to use is up to the developer, and developers will choose this. Again, you only need reducers if a final aggregation across all the mappers is required, as we had in our sales by region example. If it's important to you to break down your job outputs by temporal or organizational buckets, such that you end up with one file for every day of the week, one file for every month of the year, hour of the day, sales by region, or sales by salesperson, you can use the number of reducers to determine that, and then route your keys using a partitioner such that all of Monday's keys go to reducer 1, Tuesday's go to reducer 2, so on and so forth. The other way that you choose the number of reducers is to simply parallelize the reduce function, making it so that, for example, we have 10 reducers that complete the task in 1/10 of the time than a single reducer would. If, for example, all of the mapper output won't fit into a single reducer, we need to parallelize the function. Or if a single reducer or set of reducers simply takes too long. Again, we may end up having 1,000,000 or more mappers, and just a few hundred reducers wouldn't cut it. You have to choose one or the other. You cannot do both. For example, if you run a retail website like Amazon.com, your November and December reducers are probably going to work a whole lot harder than the other reducers, simply because you have more sales around the Christmas shopping season. Or if you want to parallelize the function across many reducers, you can't break it down by the temporal or organizational. If you're using multiple reducers to simply get that temporal or organizational breakdown, the decision is easy. You simply choose 7 reducers for day of week, 12 reducers for month of year, and so on. However, when you're parallelizing, you need to do something different. The first time that you run your job, you should simply run it with a subset of the data, maybe 5 or 10%. Try it with a single reducer or a small number of reducers and see what the output is. You can extrapolate out how many reducers you would need to complete the reduce function in a given number of minutes or hours then, and then you try it and adjust. Your first job with that subset of the data can give you a kind of back-of-the-napkin estimation of how many reducers you'll need, and then you simply need to put that estimation into action and see if your reduce function does complete when you expect. In this deck, we walk through MapReduce, what it is at a high level, how mappers work, how MapReduce works, and how the number of reducers is determined.